workshop. It's a pleasure to welcome this afternoon's first speaker, Tamara Grava, who's going to talk on universality results for Hamiltonian PDEs.
Okay, so I want to thank you, first of all, the organizer, for giving me the chance to speak here, especially after I was able to miss my talk previously during this program, so I'm very sorry about it. I want to thank you, in particular, all the Ines and Iseto for being very comprehensive, understanding, and give me another chance. So what I'm going to talk about is, some results that have been involved few years ago with Boris Dubrovin, Christian Klein, and Antonio Moro, and is concerning about universal behavior of solution of Hamiltonian PDE, in particular limits. So let me start. So what I'm considering is a subset of the general case. So I want to study and compare the semiclassical limit of the linear Schrodinger equation in one space dimension with the semiclassical limit of the focusing on linear Schrodinger equations in one space dimension. So the linear case, is characterized by, of course, we have a region with no oscillation, a region with oscillation, the transition region between, the transition behavior between these two regions is characterized by acoustic singularity, and the local description of the solution near this acoustic is the Pearcey integral. So I want to explain what is the similar picture in the nonlinear case. And the claim is that in the nonlinear case, what replaced the Pearcey integral is the Painlev&acute equation plus something else that has been identified for the cubic NLS with breeders, and in general case is not yet identified. And then this picture has been generalized to Hamiltonian PDE in one space dimension, but will be just a final comment. Okay, so this is the goal of the talk. So in the first part, I'm very quickly saying something about linear Schrodinger equation. So it's very, very standard mathematics. So we consider the linear Schrodinger equation, which I like to write in this form. And here, so we are in one space dimension, psi is a complex function, and epsilon is a small parameter. And I'm considering semi-classical initial data. So we have the amplitude and the phase S of x. And so this is a linear equation, and I can solve it exactly, and the solution is given by this integral. So this is the solution, this is an exact description, and the solution is so the integral of the amplitude of the initial data, and the phase here is contained, so the phase x is contained in this phase function here. Okay, so this S is the same as the phase here. So this is an exact solution, and the system is linear, so it's clearly integrable. And we want to describe the behavior of the solution as epsilon here goes to 0. Okay, so also this is standard mathematics. So in the limit as epsilon goes to 0, we have we apply, I don't know, stationary phase method. So the epsilon goes to 0 limit is dominated by the point where theta prime is going to 0. So where the phase here is going to 0. And in our particular case, it means that S psi, so derivative with respect to psi, minus x minus psi divided by t is equal to 0. So this is determines, so this is an equation for psi as a function of x and t. And I can write it in this form. And the solution of this equation, so you want to have only one solution. So the solution of this equation exists, so you can solve for psi as a function of t as long as the second derivative, or the first derivative depends. So as long as we make another derivative with respect to psi, so t psi s psi plus 1 is different from 0. So if this is the case, we can apply straight away the stationary phase. When the first point where this fails to be true, so when we have that t s psi plus 1 is equal to 0, then we have that the function psi as a function of x and t as a singularity in the derivative. So psi x goes to infinity, and also the second derivative goes to infinity. So we have psi xx goes to infinity. And so I want to study exactly the behavior of the solution when this happens, so in this singularity point. And this is exactly the transition regime where the solution pass from a regular behavior to an oscillatory behavior described by sine and cosine. So this regime is determined. So I'm saying I'm a little bit skipping. So by the condition that the first derivative is equal to 0, the second derivative is equal to 0, and also the third derivative is equal to 0. And this is kind of automatically because the function, so this is always, so theta prime is always positive or negative. And so this is the first point where fail to be always positive or negative, necessarily satisfy this condition. And then a genericity condition imposed that the fourth derivative is different from 0. So now, so I want to look what happened here at this point. So, and if you make an expansion in Taylor series of, we assume the initial data S to be analytic, sufficiently smooth as you like. And so it means that I can do a Taylor expansion in the vicinity of the point of the critical point T0, X0, Xi0, where we have this first singularity. And if I do this in the rescale variable x bar, t bar, and xi bar, so the phase function minus the value at its critical point is a polynomial of fourth degrees, and is given by this expression, plus, I mean, a lower order correction. And so now if you want to look at the solution, then the solution of the linear Schrodinger equation now is proportional. Here I'm skipping some constants that are not relevant for us in this moment. So, but the solution, so just doing scale analysis, so the solution is proportional up to some constant, I want to say, is proportional to this function u, which depends on two variables here. So in this way, so x bar and t bar are the rescale space and time, and we have a scaling epsilon here and epsilon here. And u is, so maybe I have to make it smaller. So u is the Pearcey integral. So is exactly the Pearcey integral. So basically near the cusp singularity, so this is called, this condition define a cusp singularity, the solution of the linear Schrodinger equation is described by the Pearcey integral. And if you ever come to Bristol, I mean, you will see in physics department huge panels of the representation of the Pearcey integrals in the physics department, third floor. They are very, very huge, nice poster with all the cusp singularity. And so in this plot, I'm showing the solution of the linear Schrodinger equation for this initial data for two values of epsilon. So 0, 1 and 0, 0, 1. And you see, I mean, so I'm describing here what's happening in this region here. So so this first peak here. So the solution, so you start at, this is x and this is time. And what you see is the modulus of psi. So the representation here is psi, the modulus of psi. And so as long as, so the description of the first singularity for the semiclassical limit is described by, so the Pearcey integral, and is plot, so is this peak here. And this is exactly, so this is just cut and paste from the NIST digital library. And this is the plot of the modulus of the Pearcey integral from two different, from top and from an angle perspective. So you have this fat panettone here that describe the first few oscillations. Okay, so this is the linear Schrodinger equation, and it's a classical steep descent analysis. Now what I want to describe is the analog picture in the nonlinear case. So I want to do the analog of this picture for the nonlinear Schrodinger equation. And so the nonlinear analog, now I'm considering the nonlinear Schrodinger equation as a prototype example where V is a function which we consider smooth, and we want that V of 0 is 0 and V prime of 0 calculated at 0 is bigger than 0. For example, you have to have in mind, for example, that V can be, for example, V of psi square is equal to psi to the k, okay, modulo of psi to the k. Okay, so there are many PDE results for this kind of equation, and so for quite general V, so the Cauchy problem is locally well posed in H1. Then for the cubic case, well, we know that the equation is integrable. This was Zakharov-Shabbat, I mean, and the Cauchy problem is globally well posed. I mean, here the contribution are many people, and probably I just put dots to indicate many people. It depends which norm you're looking for, H1 and so on. But okay, so this is so if we consider instead strong nonlinearity, not V of rho equal to rho, but for example already V of rho equal rho square, the solution of the focusing NLS may blow up in finite time, and also here there are many results. So Sulan, they find a very nice way to detect the singularity numerically. Raphael and Merles, I mean, first Tsutsumi showed that the solution blow up in the H1 norm, and Merle and Raphael show that the rescale solution in near the so that the solution near the singularity has a universal profile. So near the blow up point has a universal profile. Okay, so our goal now is to study the behavior of the solution as epsilon goes to 0. Near what I call the caustic point, and probably I should put only one point because I consider only the first point, and I will explain what I mean by caustic point, but it's the same point that I consider for the linear Schrodinger equation. So the first point is the first caustic point is the point of transition between regular behavior and oscillatory behavior. Okay, so let me now explain a little bit of history. So I will consider initial data of this form. So this is our A is just WKB data. So A is as a single hump initial data, and X is again regular analytic. And for our case, I mean, for what I want to do, we need to have both A and X analytic. And in this case, the limit has been studied by several people. Again, there are the PDE community and the integrable system community that obtain different kinds of results. So several people have studied the limit, the semiclassical limit before the formation of any caustic point, and also in more than one space dimension. In the integrable case, the limit has been studied before and after the formation of caustic. And this was a result of Canvisi, McLaughlin, and Miller, and then also for certain class of initial data by Tobis, Menakid, and Zhu, and Jenkins and McLaughlin. So what I want to say is that in the integrable case, the nonlinear oscillations are described via theta function. Now, again, I want to describe instead the transition region between regular behavior and oscillatory behavior. Okay, so I'm showing a plot here. I wanted just to stress, I show both the plus and minus case. So this is the integrable case. The plus case is called focusing, is what is the content of my talk, and the minus case is called defocusing. Indeed, you can see the different effects of the two signs. So in this case, this is the initial data. This is the value of epsilon. And so again, here it's not, it doesn't fit the plot, but on this side you have the time, and here you have X, and again X and time. And these two solutions have the same initial data. So this is the modulus of psi that is plot, and this is the same. So you can see here it looks almost like 0 compared to these bigger peaks. So the focusing case, this bump get broader and broader, and then you get oscillation here. While in the focusing case, that is the case we are going to study, you have the initial bump here that almost look flat, and then it starts to focus, and then you get these high peaks. And so again, I'm going to describe behavior of the solution near these peaks. Okay, and so let me start. So I need to change a variable to describe describe the solution, and I'm going to what they are called Magdalene transform, Oslo variables. So we take as a variable the modulus of phi square and the phase. So the epsilon, the imaginary part of log psi derivative with respect to x. And in this variable, the focus in NLS can be written as a coupled system of equation for real variable now rho and w. So the variable rho and w become real, and the focus in NLS is these two equations. Okay, so as long as gradients are small, if the gradients of the derivative means of rho with respect to x is small, and this epsilon is very small, you can disregard these terms. And so, this is indeed the semiclassical limit. And so if we disregard these terms here, and this can be done as long as gradients are not very big compared to epsilon square, then the semiclassical limit of NLS can be approximated by this system of two equations for w and rho. And the data is given here. So rho is a square and w is s of x. And this has been obtained by making, of course, the WKB answer. So we are taking the terms of order 0. Now, the first goal is to solve this system, show that it has a singularity, and show that near the singularity for this system, the solution of the full system, which is this one, the solution of the full system, will be approximated by the Painlev&acute solution. So to solve this system, I'm using integrability, okay? So, I mean, you can solve this system in many ways, but the way I'm choosing to solve it is to use integrable system. Okay, so I'm writing the system. The first thing I want to observe is that the system is elliptic because the eigenvalue of this matrix here are lambda plus minus, which is w plus minus square root of minus v prime rho, and I choose this to be positive. So the system is elliptic, so lambda plus and lambda minus are complex. And so just to say that if the system is elliptic, the initial value problem for this system is well posed only for analytic initial data. And so that's why I'm choosing analytic initial data. So this system, so I want to solve this system, and I'm choosing to solve it using integrability. So the system has a Hamiltonian structure, and so I can write this system in Hamiltonian form with H0, this Hamiltonian here, where W is related to the potential V by W prime equal V. And then we can write the equation of motion in this form. So rho t plus dx, the variational derivative of H0 with respect to W is equal to 0, and the same for Wt. So in this case, since there is no derivative, the variational derivative is simply so this symbol here means simply the derivative of the density with respect to W, and the derivative of the density with respect to rho. So the claim is that the system is integrable. So this system of equation is integrable. And indeed, for any smooth function f of rho w that satisfies this linear equation, then I solve this equation, and I write this Hamiltonian h of f, which is f of rho w in dx, and this is a conserved quantity. So basically, I can build a complete system of symmetry, so of conserved quantity, using solution of this equation. So you get so you get a complete system of solution, and so you can show integrability. Okay, so there is another property of the system, that is the solution. The system has the property of being Galilean invariant. And so if you find a solution rho and w, and you do this shift, then this, so x minus beta t, you call it rho beta, and w2 is w of x minus beta t plus beta, then this is still a solution. And what you have is that, okay, this is a symmetry clearly, and it has an infinitesimal generator that I call h of g. And this is the generator of the Galilean symmetry. Okay, so I create a family of conserved quantity, which I call HF, and the HG, the Galilean symmetry. So the sum of two conserved quantity is still conserved. So it means that HF minus HG is conserved. And I can generate the flow with respect to this Hamiltonian, which I associate to the time S. So we have the flow rho S, which is the x of delta over delta dab of this Hamiltonian, and the same for WS. And so by construction, this flow commutes with the semi-classical. So I call it's a kind of abuse of notation, but the flow below, I call it semi-classical NLS flow. It means that the flow commutes. So we can take derivative with respect to S and then to T is the same as derivative with respect to S and T and S. So we can flip the derivative and the same holds for W. So this is basically at the core of integrability. And in particular, so we can consider for this Hamiltonian the stationary flow. I want to consider the solution rho S and WS equal to 0, which is equivalent to consider up to a constant the system of equation. So the variational derivative of delta over delta rho of HF minus HT, which is exactly this equation, and the same for W. And so this is, by construction, must be a solution of the semi-classical NLS equation. And is a solution, and we can even relate it to initial data. And for some particular cases, so I mean, for some particular cases, we built in the paper with Dubrovin and Klein, the explicit expression of f of rho in W for particular initial data. So for example, when rho is equal to such square and V, this is a W is equal minus mu tanh x, we derive the explicit expression of f of rho of W from the semi-classical asymptotic, which was obtained in these two papers. So one of Canvisi, McLaughlin, and Miller, and Tobis and Zhu. And then you can obtain many other solutions because the equation for F is a linear equation, so linear combination of solution is solution. So you can build other class of solution. Okay, so we have a solution of the semi-classical system. The question is how long this solution exists. So this is the first question you want to ask yourself. And this is an easy question to answer because, okay, this is a system for W and rho, which is described, gives W and rho in an implicit form as a function of X and T. So the solution does not exist when you cannot solve, you cannot apply the implicit function theorem. So that's the way to see where the solution does not exist. Okay, so I'm describing again the system. So the solution of this system exists as long as this determinant is different from 0. So which means that the difference of these two quantities is different from 0. So the first point where this determinant is equal to 0 is a singular point for the solution, and because of signs here, so it since this f of WW and f of rho are opposite sign, it means that when this quantity is equal to 0, it means that each single term is equal to 0. So basically, the first singularity point is determined by the solution of this equation. And this point is called a point of elliptic umbilic catastrophe. And so we have three equations. So these two equations depends only on W and rho. And so solving these two equations, you get a point rho 0 and W0. Then you plug it here and you get the time when the singularity occurs. And then you plug it here and you obtain the point x0 where the singularity occurs. Okay, so we have then this point is the singular point for the solution of the semiclassical NLS system, and it's a point of it's called a point of elliptic umbilic catastrophe. So let me describe the singular behavior of the system near this point. So what I'm going to do, so I'm calling x0 and t0 the singular point, and ρ0 and w0 the value at the singular point. Then I'm considering the scale variables, so rho minus 0, w bar w minus w0, and so on, t bar t minus t0, and so on. So I'm considering the previous system, which I solve exactly, and I'm expanding in Taylor series, and this is I can do because I'm considering analytic initial data. And I'm doing a scaling. So the scaling here is important. So x goes to alpha square x, t goes to alpha square t, w goes to alpha w, and rho bar goes to alpha rho bar. And then I'm letting alpha goes to 0, and then the system that I was describing was a system of two equations. I pack it in a complex equation. So the solution of the semiclassical NLS turns into this equation. And you can take the complex conjugate as well. So is alpha is a constant, and lambda 0 plus is a constant, non-zero constant. So is alpha r square equals z. Okay, so this is basically what is called the force singularity. So we have and of course you have also the complex conjugate system. So you have also the complex conjugate system. So you have alpha square equal x bar. So because we start with a real system, so two equations, and now I have one complex. So you take the complex conjugate. Okay, so this is what is called the force singularity, and the system, I mean, as a singularity. So it means that in our semiclassical approximation, we disregard the terms containing epsilon. Now we have to take care of them. So we cannot anymore ignore all these terms containing epsilon. So now I have to take care of of the terms containing epsilon. And so let me start with the terms containing this epsilon. Okay, so before I was considering only this Hamiltonian here, and now so I'm to not make things too heavy. I should have put a superscript epsilon now here, but I decided not to put, otherwise notation was getting too heavy. So now I'm rewriting the generalized nonlinear Schrodinger equation in this form for the variable rho and w. And now the terms containing epsilon in the Hamiltonian is here. And again, so w prime is equal to v of rho. So the equation of motion now contains epsilon because they are here. And so this is written for rho and for w in this form. Okay, now I don't have integrability, and as I had when epsilon goes to 0, I showed that the system was integrable. Now for when I add in this dispersive term, the system is not anymore integrable except when v of rho is equal to rho. And so this gives the cubic focusing NLS equation. So in this case, there is no integrability, but I still want to build an approximate solution. And for doing this, I'm using this idea of approximate integrability, which is explained in these slides. So I'm repeating exactly the procedure I did for the dispersionless case. I first consider the Galilean symmetry that gives me one conserved quantity, and then I consider a family of approximate conserved quantity, which I called H epsilon of f. So again, so I have one symmetry, which is the generator of the Galilean symmetry. And then for every function f of rho w, which satisfy this linear equation where v is the same potential as this one. So for this family, I build a set of approximate symmetries. So this means, what does it mean, this expression? So it means that So if you consider, so it means is approximate conserved quantity. It means that the commutator between the Hamiltonian H and this H of F epsilon is equal to O of epsilon cube, okay? So it means I'm able to say that so the term of order 0 and epsilon is 0, the terms of order epsilon is 0, the terms of order epsilon square is 0, and the first term is 0 term is order epsilon to the cube. So this is what I mean by approximate symmetry. Okay, so this is the way I'm building the symmetry, and now I'm applying the same ideas I use for the dispersionless case. So I have Galilean invariance, and this approximate symmetry, and I'm considering again, so the linear combination of HF of epsilon minus HG. So this is a conserved quantity up to terms of order epsilon cube. So I can generate this flow for rho s. So I introduce a time s and w. So I consider this evolution. So this gives a flow, and then I can say that this flow commutes with the generalized NLS flow up to terms of order of epsilon. Then I consider the case the stationary flow as before. So I'm considering the stationary flow. So it means rho s equal to 0 and ws equal to 0. And so it means in particular, so that this quantity is equal to 0. And so almost at a constant. And so I'm considering this equation. Okay, now this equation, since we have an epsilon here, now this equation contains an epsilon. So when epsilon equal to 0, this equation coincides exactly with the solution of the semi-classical NLS equation. Now that epsilon is different from 0, we have really an ODE. Okay, so we have this is an equation which contains x and t explicitly, and then as terms that are contains the derivative with respect to x of rho with respect to x and w with respect to x. Okay, I'm not going to write this equation explicitly, but what I want to say is that we have an equation here that contains several derivatives. So maybe let me go back of one slide. So you do now the variational derivative, and so okay, the first term here, this gives the same contribution that was obtained in the semi-classical limit. And then you have the contribution, all this contribution coming from the approximate symmetry. So in this case, so we have rho x square here, wx square, and rho x and wx. So what I want to say is basically is a polynomial of degree 2 in rho x, and wx is a homogeneous polynomial of degree 2 in rho x and wx, this contribution. So this is the important part to do the expansion that I'm going to talk in this next slide. So you have this structure, and then what you do, so you get an equation here when you do your variational derivative, you get an equation, and then you do the following. You expand it, the equation near the singular point, x0, t0. This was the singular point for the solution of the semi-classical NLS equation. Then we apply the same scaling that we apply for the semi-classical NLS equation near the singular point. But this is not enough. We need to apply also a scaling to epsilon. And so we apply this scaling, and we let epsilon goes to 0. Then if we do all this gymnastic, then the equation 4 turns into what is called the Painlev&acute equation. Okay, and so this is a very general fact, and but the most important, part here, is to recognize, so to identify the scaling. So the scaling is the most important part. So The way we scale is the way that gives us the Painlev&acute equation. And the scaling are obtained from the singularity structure of the semiclassical system. Okay, so we have the scaling, and the scaling were identified by the singularity structure of the semiclassical system. The only scaling that was not immediate is this one. So we have the scaling, we expand the system, this system near the singular point and scale out, and what you remain is with the Painlev&acute. Okay, so this is the conjecture. So for the focus in NLS was conjecture in 2009, and for the most general case was conjecture in 2015. So, and the conjecture is as follows. So the solution, which I'm compactifying in this R. So I'm taking the combination of W and ρ. So the solution R of this generalized focusing NLS equation. So, and this is, is the description near the point of formation of singularity. So near the point of elliptic umbilic catastrophe for the semi-classical NLS is described up to shift and rescaling by the solution of the Painlev&acute equation. So here you recognize the Painlev&acute equation. So the Z variable of the Painlev&acute equation is connected to space and time by this change of coordinate. And so this was the conjecture. So in the 2009 paper, we also identify which, so the Painlev equation, is this one clearly, but we need to identify the solution. So the solution was uniquely determined by this boundary condition. So basically we want that when Z becomes very large, these terms become negligible. And so we reach the semi-classical solution, which is going like square root of Z over alpha. As Z goes to infinity, and and this is also for the argument of size, since we need to rescale. So this is Painlev&acute not in standard coordinates. So to come to this 4/5, I need to rescale. So to shift Z by this constant, where this alpha and beta are exactly this alpha and beta. So we want the argument of zeta less than 4/pi. Okay, so the conjecture, in the 2009 paper was that also this solution, which is called the three-truncate solution, and this is the Boutreau solution. So we claim that this solution was smooth in the whole sector, of the complex plane delimited by argument of zeta less than 4/5. And this fact was proved by Costin, Wang, and Tanvir in 2014. Okay, so let me say a few words about the proof of this conjecture. So what has been done for proving this conjecture? So, and maybe I want to say first a few words about the three-truncate solution. So this three-truncate solution has pole in the remaining sector. So here, so in the argument for argument of zeta bigger than 4/pi, the solution has pole. So here actually we have different signs with respect to my convention. So in my notation, these are the pole of the Painlev&acute solution, which are taken from the paper of Fromberg and Weidemann. But my convention is that you have to flip this image, reflect this image with respect to the imaginary axis. And in my convention, the poles are exactly on the negative real axis. Okay, so this are the pole of the Painlev&acute, and this is the solution of the cubic NLS for specific initial data. And so the description that so you see that there is a kind of one-to-one map between these peaks and these peaks here. And the description of the Painlev&acute asymptotics holds basically before the formation of the first peak. So basically, the first peak here, the first dot that you see, which corresponds to this dot, corresponds to a pole of the Painlev&acute solution. And so the poles are described, the poles of Painlev&acute are described, so they start with Z minus ZP. So if P is a pole, the solution near a pole has this expansion. So you have an infinite series here. And so I mean, I'm not sure I'm complete with this list of people, but so the first pole that I know was determined by Cauchy was the first pole on the negative real axis in their notation, so it's the first pole here. Then Mazzoero determined the poles using WKB analysis, and Novoksheno, I think, using PDE approximation. Fomber and Weidman, I mean, they implement a very precise numerical code using PDE approximation. And I think Dali and Tanvir were able to determine the pole using resurgent methods. And I put dots because I'm not sure I'm mentioning all the people that have been involved in this, in studying the poles of the three-truncate solution. Okay, so now let's go back to NLS. So I want to complete the description. So I want to complete the analog of the Pearcey integral for the nonlinear case. So Pearcey integral is linear equation, Painlev plus something else is nonlinear equation. So let's go to the results. So in this case, I mean, Bertola and Tobis entered the game. So Bertola and Tobis, in this very nice paper in 2013, they showed that they proved the conjecture that we made about the behavior of the solution of the cubic focus in NLS, so the integrable cases. And they were able to show that at the onset, so near the first singularity for the semiclassical solution, the approximate solution is described by the Painlev&acute equation. However, the Painlev&acute solution does not hold at the poles. And so what they were able to show is that the apposition of the poles, so the pole position for the Boutreau solution, the cubic NLS equation is approximated by breeders. So basically the points, the big peaks that we see in the solution are breeders. So while in the linear case, this big panettone was the Pearcey integral, and this was enough to describe the whole asymptotic. In this nonlinear case, we need two objects. We need Painlev&acute on one side, and at the poles, we have to measure the Painlev asymptotic with breeders. So, and for example, if I take the rho, so the modulus of the amplitude of the solution of NLS, the breeder, and I'm putting only the modulus. So the breeder is the description of Bertola-Tobis is the following. So the solution is approximated in this formula that is basically the breeder plus an error for the epsilon 4/5. Here I recall what is Z. So Z is this rescale variable. So X0 here is the point of singularity for the semiclassical system. So this result is very beautiful because does not depend on the initial data. So basically it's saying that the peregrine breeder is generically a global attractor for the semiclassical limit of the NLS equation. It's a global attractor. Whatever you start with, the solution in the semiclassical limit asymptotically behave like a breeder at the first peak. This is basically the analog of the result of Mer and Raphael, where they describe the universality behavior of the blow-up solution of NLS, saying that it's up to scaling is the soliton. So they describe this the blow-up behavior as a soliton. In this case, in the semiclassical limit, the equivalence is the breeder. So the breeder, I want to stress, is a global attractor for the NLS, semiclassical NLS solution. And just observe this expression. So first of all, when Z goes to infinity, the solution rho tends to rho 0 because this terms in the denominator is dominant. So it means And so this is for fixed z, you let epsilon goes to infinity. So we look at the semiclassical limit. So it means that you can disregard this term. And so you basically converge to the semiclassical asymptotic, which is for 0. And now the highest, so the highest value of this solution is given when z is equal zp. And so this, so when z is equal to zp, this and this goes away, and here remains 1 minus 4, which is equal to 3 square is equal to 9. So it means that the solution is 9 rho 0. So which is approximately 9 times the critical value. And this is the reason why we see these very high peaks. So if we look at the modulus square, we have 9 times. If we look only at the modulus, we have 3 times. So, but it's a big increment of the background. So you go 3 times or 9 times with respect to your background, according whether you look at the modulus square or the modulus. Okay, so this is what I want to say. Let me comment further. So basically, yes. So basically, at each, if I call XP and TP the position of each pole of if XP and TP is the position of each breeder, so this breeder is related, for example, to the poles of the Painlev solution by this formula. So ZP, pole of the Painlev, is equal to this rescale quantity, which is my shifted quantity in space and time. So in particular, for example, if you take the first pole of the three-truncate solution, you get the position here. You can get solving this equation. So you can get XP and TP. Okay, so this result I think is very nice. And so after the paper of Bertola was completed, so we write with Dubrovin, Moro and Klein another paper for general elliptic and hyperbolic, so general Hamiltonian system into components whose limit, semiclassical limit is hyperbolic or elliptic. And we came up with a similar, analogous conjecture, which is a little bit on the steps of this. This is a theorem regarding the solution of the Cauchy generalized NLS equation in particular. So if we take the potential V of rho is equal rho to the K with K bigger than 1. So in this case, and you think of K integer now. So the solution of generalized NLS equation has a blow up in finite time. So the norm blow up, the L2 norm blow up. And Mer and Raphael in 2004 were able to show even the blow up profile of this equation. However, what is completely unknown despite the literature on blow up is huge. There is, at least to the best of my knowledge, there is no way of saying when the blow up occurs. So you don't know, so you know that there is a blow up because you study norms and you saw that there's some norm blow up, and so you are able to say that there is a blow up, but you don't know when the blow up occurs. And what we did is to conjecture that the solution of the generalized NLS equation exists. So in the semiclassical limit, of course, epsilon goes to 0 for all time less than TP, where TP is where this and the blow up occurs at the time TP, where this TP is exactly the solution of this equation here. And so this is the first pole of the three-truncate solution. Basically, the claim is that when the equation is focusing, as soon as it starts to focus, for the cubic NLS, you have the breeder, and while for the other, for the generalized NLS, you have blow up. And so we test in this paper this conjecture, and we test numerically this conjecture, and we confirm this behavior. So here I want to say that there is a scaling. So there is a scaling in epsilon of the blow up time. So we were able to detect this scaling. the blow-up time. So the scaling in epsilon of the blow-up time is compared to T0, where T0 is the time where the semi-classical system has a singularity. So this can be determined analytically. And this TP has a dependence on epsilon 4/5. So we were able to, at least, I mean, we determined several blow-up time as a function of epsilon. We were able to show that this behavior occurs. Unfortunately, I mean, this observation has completely been unnoticed, but I think it's a very nice observation concerning blow-up time for generalized NLS equation. Okay, so yes, another thing about yes, persistence of breeders. Okay, so as I said, the solution of NLS in the semi-classical limit, I mean, is described near the first singularity for the semi-classical system by the Painlev&acute plus something else. For the focusing case, the cubic focusing case, we know that we have a breeder. So we have this breeder here. For the general case, it's not clear what needs to be considered. But in these numerics that I've done several years ago, I want to show that, I mean, basically this focusing behavior is persistent. So here I'm considering a perturbation of the focus in NLS with a dispersive term, so full derivative and a stronger nonlinearity. So, and I'm considering epsilon equals 0.05. So when we have alpha equals 0 and beta equal 0.05. So I'm comparing the solution of focusing. So here in red is the solution of focusing NLS, and in blue is the solution of the perturbed case. So here in blue, you see you have a little bit, not very big because it's 0.05, you have a stronger nonlinearity. So it means that you have a little bit higher focusing effect. And so it looks like the behavior is still a kind of breeder, but I mean, there is no even an answer for this behavior. In this case, we put the beta, so the nonlinearity 0, we take a stronger dispersion. In this case, you see that the breeder of focusing NLS, which is in red, so the aberture case is bigger, and so the dispersion has an effect, but you still see a focusing of the solution near the formation of the peak, of the first peak. Okay, so the idea is basically that something that should look like a breeder should describe in a more general setting solution of perturbation of focusing NLS. Okay, so some remarks maybe so about this result. So I described this result for the focusing generalized NLS equation, but we derived this description for a much broader class of Hamiltonian system, and basically, so it's where Hamiltonian system into components whose semi-classical limit is elliptic. And so I want to say also that this description, so that the description basically obtained by Bertola and Tobis, where they study semi-classical limit of NLS, and the asymptotics is obtained by Painlev equation and breeder has been, I mean, so the analog of this description, and this is rigorous mathematical result, have been obtained for the Sine-Gordon equation by Peter Miller and Bing-Ying Lu in a very recent paper in 2021. And so they study the semi-classical limit of the Sine-Gordon equation. And so again, they obtain, so they showed that the Painlev&acute tritroquet solution described the evolution of the Sine-Gordon near the first caustic singularity. And this is slightly different from the theory that we develop in this paper, because in this case, the equation that have a singularity is not the Sine-Gordon itself, but is the Witten equation for the Sine-Gordon. So it's slightly different. So this Witten equation approximates again the solution of the Sine-Gordon of the semiclassical limit. Then, like in the Bertolottobi's paper, they showed that when the three truncate solution are smaller, you have to obtain a particular solution of Sine-Gordon to match the behavior of the semiclassical limit at the poles. Okay, and from this is only numerical, so a similar picture, a similar picture from this paper has been obtained, numerically for the small dispersion limit of the focusing KP equation, Kardashev-Petriashvili equation. So in this case, we obtain a similar picture of this paper. So you have these very big peaks that are formed. So so it looks like at least qualitative, the structure that we have in one space dimension persists in two space dimension. Okay, so maybe I'm a little bit, okay, so I'm just in time. So just to summarize, I want to say that, the message that I want to pass to you is that when you solve the semi-classical NLS equation, linear NLS equation near the caustic, so you have to use the Pearcey integral. So what is the nonlinear analog of this setting? So this is the whole message I want to send you. So the nonlinear analog of this setting is Painlev&acute plus some particular solution of the PDE you are considering. So the Painlev&acute is universal, while this particular solution is universal in the sense that is a global attractor for the equation. It does not depend on the initial data, but it depends on the PDE. The Painlev&acute is universal in the sense that it does not depend on the initial data nor on the PDE, while the particular solution that one needs to put there depends, of course, on the PDE. So thank you very much for your attention. So I'm done.
Thank you, Tamara. Are there any questions? And John?
Yeah, so is it right that all the cases you considered include integrable special cases?
Sorry, can you repeat, please?
Yeah, is it right that all the examples you've considered have integrable PDEs as special cases? So yeah. if there is a universality.
Well, yes, we want integrable PDE which are local. We have a local Hamiltonian structure, yeah, an evolutionary type. So Sine-Gordon the Sine-Gordon doesn't fit our. So Sine-Gordon is not in our class. Sine-Gordon is not in our class because of the second derivative. But so what we consider here as integrable, yeah, is yes, local Hamiltonian structure and evolutionary. So I'm not sure that non-evolutionary.
If there's universality in a class of problems that have integrable special cases, Painlev&acute is not surprising. Have you considered any classes which do not have integrals?
Well, I wouldn't call it not surprising, since Painlev&acute doesn't solve any of these equations.
No, but if there is no DU reduction, it's not surprising it's Painlev&acute.
Yeah, it's not surprising that it's Painlev&acute, but it's, I want to stress, this is Painlev&acute won't be a solution of any of the equation I'm considering. Mm-hmm. And
yes, I'm not to downplay your results. I'm interested in a more general question, which is, if you can, have you ever looked at any classes of PDEs that do not have integrable equations as special cases within the class?
Well, but this is full. All these class that I'm considering, you don't need to have, look at this. So this is not, so this is not integrable.
No, but k equals 1 it is. So if you have integrability, then you would expect.
Yeah, sure, but my result holds for any k, and it's not integrable in any sense.
We're across purposes. You're saying the result is universal. If there's an integrable special case, then the universal result must be integrable. I'm asking a different question. If there's a class which doesn't have any integrable special cases.
Yeah. You can have. I mean, yes, you can have. I mean, in the class we consider. Yes, we consider. Sorry, maybe let me come back. So we consider any Hamiltonian. So yeah, we consider any Hamiltonian. So the class we consider. Let me write it here. So we consider. So the case we consider was a Hamiltonian system, which are of the form. So ABC, so C of rho of W times WX squared. So this is the general Hamiltonian system you consider. So you see, I mean, this is generically is not, and so it's not integrable. So and maybe you can find system. I mean, so there is no way you can find always an integrable reduction. Of course, if you choose particular values of A, B, and C. So this is for any values of A, B, and C.
Yeah, we are across purposes. I've taken up too much time, so I'll shut up.
And so, of course, there are cases where you have non-local structure for sure probably there is no Painlev&acute. One of these cases has been treated in one spatial dimension for hyperbolic system by Mazoero and Coulter, where they find an integrable version of the Painlev&acute. So a generalization, so non-local. Yes, but this was a non-local structure, so non-local equation.
Thank you. Thank you.
Are there any other questions? If not, it just remains to thank Tamara for a nice talk, and
Thank you very much.
reconvene at 2:45, 13 minutes.
So now I need to stop share.